It's now time to build some intuition. To do so, let's return to our mathematical expression for the discrete time Fourier transform. What is this expression actually doing? To answer this, we'll consider each piece of this equation. The first term represents a sum over the indices of our variable x sub n. Because each subsequent index represents a step forward in time of size delta, this sum represents a sum over time. In fact, this sum extends from the first index, n equals 1, to the last index, little n equals big N, of the data. So the summation occurs over the entire duration of our EEG recording. Adding the second term, the summation now acts on the data, x. So what we're doing is summing up the data over all indices, or equivalently over the entire time of the recording. The third term is a mess. It consists of an exponential operating on the product of 5 individual terms, each of which is a number. The first two numbers are simple, minus 2 pi. The third number is I, which is equal to the square root of minus 1, a strange quantity representing an imaginary unit. The utility of the imaginary unit is that we can rewrite the exponential as the sum of a sine and cosine function. Remember from calculus the remarkable Euler's formula, which relates our complex exponential to a sum of cosine and sine functions. Notice that the I now appears multiplying the sine term, and not inside of the arguments of either sinusoid. Both sinusoids operate on the product of 2 pi and the two terms, the frequency, f sub j, and the time, t sub n. Rewriting our equation for the Fourier transform using Euler's formula, we find a new expression. This expression consists of a cosine and sine term, and here we have distributed the summation over both terms. Written in this way, the Fourier transform becomes easier to interpret. Let's consider the first term in our new expression. For each index n, we multiply our data, x sub n, by a cosine function evaluated at frequency fj and time t sub n. We then sum the results of this multiplication over all time indices, from n equals 1 to n equals big N, or equivalently from time t sub n equals delta all the way up to big T. So, in words, we multiply the data by a cosine function at frequency f sub j for each point in time and sum the product over time. The second term is like the first, except we multiply the data x sub n by a sine function. We can therefore think of the Fourier transform as comparing the data x sub n to sinusoids oscillating at frequency f sub j. When the data in sinusoid at frequency fj align, the summation in the Fourier transform is large, and the result, big X sub j, is a large number. When the data in the sinusoid at frequency f sub j do not align, the summation in the Fourier transform is small, and big X sub j is a tiny number. In the next video, we'll make these ideas more concrete through a simple example.